Okay guys, so we are continuing our class, and if you remember that I was solving a long real 3D robot. That's right, if you remember from part 14, right? It was this robot on part 13, so it is a long problem of the robotics. So we have 3D robot in this and 3 degree of freedom, if you remember from the previous class, and we had these, and you're gonna see this exactly on the Matlab code. This is your base x naught is coming out. This is z naught that we have done that. Here is a1, here is a2. I'm gonna make a movie of this today in the Matlab. You are close to the end of this problem. So here is rotating as angle of theta 1. This is rotating as angle of theta 2, remember? And this rotating as angle of theta 3. By having this, if you remember from the part 13 and part 14, finally I could calculate the Jacobian matrix of this 3D robot. That because this is 3 degree of freedom system, we have 3 joints here. So let me make it a little bigger, because here we go. Here we go. So this is 6 by 3, right? This 3 for the degree of freedom system of joints. So here we got this minus a3 cosine 1 s prime 2 3 plus a2 cosine 1 s2, and you know what is cosine 1 sine 2, I explained, minus a3 s1 s2 3 plus a2 s1 and s2, and here was 0 0 0 1. Second line was minus s1 in a3 cosine 2 3 plus a2 cosine 2, and here was cosine 1 a3 cosine 2 3 plus a2 cosine 2. Here third one was minus a3, right, minus co1 square s prime 2 3 plus s1 square sine 2 3. You have your notes from part 14. Fourth line is a2 s2, and this is minus 1 2 3 4 5 6 1 2 3, and here minus cosine 1 minus sine 1 and the 0, and the last line I have to move it a little, and the last line J3, say here is J3, was minus s1 a3 cosine 2 3 cosine 1 a3 cosine 2 3 a3 cosine 1 square sine prime 2 3 plus s1 square s2 3. That's right. Again minus cosine 1 minus sine 1 and the 0. Remember, this was, for God's sake, J1, this was J2, and this was J3 that he calculated, right? At the end of the day, I told you this kind of relates the translational velocity of the end effector Vx, Vy, Vz in the base coordinate system, and the omega x, omega y, and the omega z, you can obtain them in J multiplied, you have 3 degree of freedom, theta dot 1 links, joints angular velocities. This is 6 by 3, this is 3 by 1, because we have 3 degree of freedom system, theta 1, theta 2, theta 3. So you can get this. So, and this is forward kinematics. By having this, you get this. This is forward kinematics. forward, as I taught you in the class, is forward kinematics. You have the angles of the joints, kinematics. Now you want to calculate the velocities of the vector, translational velocity and angular velocity. So again, remember that when I say cosine 1 means cosine of theta 1. When I say sine 1 is sine theta 1. When I say cosine 2 means cosine theta 2. When I sine 2 means sine theta 2. Cosine 3 I say cosine theta 3. When I say sine 3 I say sine theta 3. For those of you who forgot from the previous classes, and these notations, I don't want to make a mistake. When I say S23 in this Jacobian matrix, means I say S2 cosine 3 plus S3 cosine 2. When I say S prime 2 3 means S2 S and cosine 3 minus cosine 2 S3. And when I say cosine 2 3 means cosine 2 cosine 3 minus sine 2 sine 3. And I will say cosine prime 2 3 means that sine 2 sine 3 plus cosine 2 cosine 3 in the Jacobian matrix. Now we have everything. What I'm gonna do, so I have to provide these angles because I'm going this way. I need the angular velocities of the joints and some angles here, sine theta 1, sine theta 2, cosine theta 1, cosine theta 2. So I'm providing this by myself. I'm saying, because I want to develop the code in Matlab, right? I'm saying, let me see what I wrote here. Let me look at my notes. I want to be consistent. So I'm saying, I say theta 1 is A1 sine t is a periodic, going back, forward, backward, forward, backward. So theta dot 1, for God's sake, gonna be how much? A1 cosine t, t is time, that's right. And say theta 2 is A2 cosine t, has a phase shift. So theta dot 2 gonna be minus A2 sine t. And I say theta 3 is A3 again, different amplitude with the A1. So and theta dot 3 gonna be A3 cosine 3. Here we go. I'm gonna replace this in the Jacobian, in here and in the Jacobian. Now let's go to Matlab. Okay, I already developed the code. I'm just gonna explain part by part to show you how you implement the Jacobian in the. This is primary step that I'm explaining to you. Okay. Then, when you go to grad school and become a researcher, you can expedite everything. Okay. So here we go. Okay, in the top, always in your codes that I taught you previously, say clear all and the CLC. CLC clears the workspace of your code. Remember, like here, like I say A is equal to 2. Now I say CLC means clear, everything gone. And the clear all, it's gonna clear the parameters that you ran in your workspace. But exactly based on what I was saying, the links, lengths. That's right. Look at here. What happened? Okay. See A1, A2, A3. Actually, this A1, A2, A3, I'm naming it A prime because I don't want to get confused with this. Right, A prime. So here I'm defining from the code, see, links. I'm saying the first link is 0.2 meter. Obviously these are in the meters. In meters. I'm commenting, that's right, in meters. Point is 0.3 and 0.3. So I mean the link to a link here, they have the same links and they are different from the link. So con means counter. I'm going to explain it to you later. Time step. I want to just simulate your system, that's right. And the final time gonna be 20. So as you know from Matlab course that you can make for a loop because I want to make a simulation of this robot. So T time, because we'll be using time in this angles and angular velocity of the links that I'm giving to you, that's right, is from 0 and the time step is 0.05 to final time. Then I'm saying con is called count plus 1. I will teach you what is this. Now here I'm saying angle and angular velocity of joint 1. I'm saying amplitude 1 is 0.8, theta 1, look at here, theta 1 is amplitude sine theta, exactly as I wrote in the PowerPoint. So d theta 1 is derivative theta 1 is amplitude cosine of this, as I did. Then I'm putting these angles in a counter to make a matrix of, to make a vector of angle 1. This is how we make a vector by consecutive numbers. Now let's go to the angle and angular velocity of joint 2. Again, I'm going to assign a different amplitude, 0.7. Theta 2 is amplitude cosine theta. Look at here. Cosine t, exactly this. That's right. Theta 2 is again minus sine amplitude, and I'm putting there again. And then angular velocity of joint 3 gonna be different amplitude, 0.4. Again, this is different from amplitude 1. So amp3 sine 3, dA3 is this, and we're done. Now exactly redefining cosine and sine of the angles as I did in the derivation of the Jacobian matrix. I said cosine 1 is cosine theta 1. And you have cosine theta 1 from here, so I put time here, gives you theta 1. Put time here, gives you theta 2. Put times here, gives you theta 3. Now I'm defining cosine 1 is cosine theta 1, cosine 2 is cosine theta 2, cosine 3 sine 1, sine 2, sine 3. This is the powerful ones of the Matlab, right? And exactly if you look at here, guys, S23 that we have in Jacobian matrix, S prime, cosine 23, cosine 2 prime. We need in Jacobian matrices, right? So S23 is now, because we define sine of theta 2 as sine 2, like here, cosine theta 3, exactly based on whatever we taught. See? For example, S prime, see? This is S23, this is S prime 23, is sine 2 cosine 3 minus sine 3 cosine 2, look at here. S prime is sine 2 cosine 3 minus cosine 2 sine 3. Here we go. Right? And cosine prime is going to be, see, it's going to be as we did. Now, Jacobian elements. If you look at here, we have J1, we have J2, and we have J3. I'm defining J1, J2, J3, exactly like this. J1 is minus, if you look at your notes, minus of A3 in cosine 1 sine prime 2 3 plus A2 cosine 1 sine 2. This is the first element of that, exactly like this. See, exactly like this. And the second element, minus of this. Look at here, minus of A3 sine 1 sine 2 3 plus A2 sine 1 sine 2, and 0 0 0 1. exactly like this. 0, 0, 0, 1. Here we go. Right? Now let's go to J2, because I'm double checking with you at the same time. Minus S1 A3 cosine 23 plus A2 cosine 2. Now cosine 1 A3 cosine 23 plus A2 cosine 2 minus A3 sine 1 square sine 23 minus cosine 1 square S prime 23, right? Minus A2 sine 2. Look at here. Here we go. This is one line. So right, minus A2 sine 2, right? Minus cosine 1 minus sine 1, 0. Look at here. Minus cosine 1 minus sine 1, 0. Now J3. J3 is again minus S1 A3 cosine 23 cosine 1 A3 cosine 23 A3 sine 1 square S23 plus cosine 1 square S prime 23 minus cosine minus sine 0. Now this is Jacobian matrix. Here we go. See, Jacobian matrix. Jacobian matrix is J1, J2, J3, exactly as we did here. You got it. J1, J2, J3. Putting together gives you the Jacobian matrix of this 3D robot with 3D degree of freedom system. And now vector of velocity. So, and as you see here, as I wrote here, V is J in this theta dot 1, theta dot 2, theta dot 3. So V total, this is vector, is J Jacobian matrix in theta dot 1 as we defined above. Next row theta dot 2, next row theta dot 3. Exactly, I'm following from whatever I developed analytically. See, theta dot 3 based on whatever I defined here. So now translational velocity, because as I taught you here, guys, oops, what happened? Okay, as it's recording, yeah. As I taught you here, guys, this is 6 by 3 in 3 by 1, gonna be 6 by 1. Let me write it here. 6 by 1. So first row, first column gonna give you Vx of the end effector. Second row and the first column gives you, this is gonna be first row, first column. This is gonna be second row, first column of this vector. This is gonna be third row and first column, fourth row, first column, fifth row, first column, sixth row, first column. So for having this vector in Matlab, this is enough that you say delta Vx, okay, I'm putting here, put in a counter, is V11, V21, V31, V41, V51, V61. Okay. Why I'm putting in the vector? Because I'm gonna plot it together. Okay. So this part of the code is making a movie of that robot, and you're gonna see. Because I'm in the 3D plane, I'm gonna connect, guys, these lines, this point to this point, this point to this point, and this point to this point. So if you want to plot a line in Matlab, you have to give the 3D coordinates of this point and 3D coordinates of this point. Okay, so you see that x of this point, guys, and the x of this point here is how much? Is 0, because x is out of the page respect to the base coordinate system. That's right. So you see that. Look at here, 0 and 0. This gives you the x of those 2 points. Now to the y, okay, y of this point and y of this point in the base coordinate system, because this is rotating around the z-axis. Y of these 2 points never changes, so it's gonna still remain 0 and 0. What about z? And this is z part of that, z part of those points. Look at here, guys. This point is attached to the actuator of the base coordinate system, so it never changes the z. But the z of this point in the base coordinate system is how much? In the z0 is a1. Here we go. We got that. 0 and a1. And we defined a1. That's right, the length of the link here. This is a1, 0.2 meter. Now I'm going to say, make that the line as a blue color. This is how we define blue. And thicken that line as a line width of 2. This is arbitrary, you can do that. Then grid. Okay, figure 1, grid that, because I want to see the grid and scaled a movie. Then, because we are continuing to make a movie of the second link and the third link, you're going to say to Matlab, hey buddy, hold on. This is the Matlab command to say that I'm not done with the plotting and the making movie. You have to hold on. Now going to oh my god, going to the point of this link and this link, this joint, this point and this point, to plot this line, this link of the robot. Obviously this point, look at here guys, I'm circling this point, we already had it. This point x, look at here guys, this is not magic. This point there you go. Oh, okay. This point, here we are, is 0, because we already had it here, that's right. Is 0, that's right, is 0. But this point, x is changing, because this is rotating around axis theta 1, that's right. So on the other hand, if you calculate, I assign this to you as a homework to see how you drive this. On the other hand, I say x of that point gonna be a2 sine theta 2 cosine theta 1. I want that you go one by one of these to see how I drive it. You have to do it, guys. This is practice for you. I'm saying if say point M, I say that x of M in the 3D space gonna be a2. What was that? a2 sine theta 2 cosine theta 1. Sine theta 2 cosine theta 1 with respect to this base coordinate system, and I continued y and z and too many things. Understand? So you see that the z of that in that coordinate system, so this is gonna be, get here, sorry, this is gonna be x of that point, this is gonna be y of that, and this is gonna be z of that. Here we go. Okay, it's gonna be z of that. Okay, so I want that you go and calculate that. I want that this geometry, this is not robotics. I want to make sure that you know what is trigonometry. Go and drive one by one of these. And this is for link 3, guys. This is for link 3. Okay? Link 3. And this is end effector coordinate. You see that? This plot 3 is end effector coordinate. Obviously, go and drive it. This is I'm showing with the green. So I'm showing the link 1 as blue line, as a red line, as the blue line. At the end, I'm showing the end effector point as green. Then this is x, y, z labels and the axis that you know from the Matlab. And finally coming here, figure 2. Again, I'm giving the whole time. Look at here, whole time. That's right. Now plot 3, I'm plotting the phase portrait of the velocity, kind of. I'm plotting Vx, Vy, Vz, but in the sense that we define the coordinate systems, right? So Vy, Vx, Vz, you will understand. I'm going to upload it on the blackboard. Then omega x, omega y, and omega z, based on whatever we defined here, based on the vector. Look at here, guys. Omega x, omega y, and omega z. Right, so Vx, we need a vector of that, Vy and the Vz. Okay, and we plot here, and okay, guys, if I tell you that what is look at here, guys. Yeah, guys, if I say what is the omega z of the end effector, what is gonna be your answer? I'm gonna give you 2 minutes. Don't go forward the video because I want that you think about this. Any ideas? Obviously, the omega z means rotation of the end vector based on the coordinate system of base coordinate system gonna be theta dot 1, because the only rotation is theta dot 1 around the z-axis. So that's why I want to double check my code. How? I'm just again plotting theta 1, theta dot 1. Then in figure 2, I'm saying based on the Jacobian approach, plot the omega z of the end effector and theta dot 1. They must be same. If they are the same, means that the Jacobian matrix that you have made is a right answer. At the end of the day, I want that you go based on whatever I developed here. These plots. See, this is the EE end effector coordinate. I just transfer it here. X of end effector, Y of end effector, and the Z of end effector. Then I plotted X end effector versus Y of end effector and Z of end effector in XYZ plane when the things is rotating. Now let us do that together. Are you ready? Yes? Okay, here we go. See, just by developing this code. Oh yes, this is, see that this is x-axis, y-axis, and the z-axis, and this 3D graph freedom robot based on the harmonic rotations. So this is gonna be, and then the vector is the green. That's right. In the code I saw the green, blue, red, blue. See that gonna harmonically gonna your manipulator and an effector gonna oscillate in the XYZ plane. This is a very effective tool when you become a grad student and you want to do research in robotics, because it's much better that first you make a simulation of what you are doing. Don't go to experiment, because maybe you are on the preliminary stage of the robotics, but when you design a controller for the robot, first you have to see the simulation results. Maybe it's going to damage your actuators in reality. So simulation is the immediate part of the robotist. Okay, see that? Now it's simulating for see 20 seconds. That's right. Here we go, 20 seconds. right? And now this is what? This is the x exactly based on, look at here guys, I'm not crazy. This x is out of the page, y is like this, z is out, up. X is out of the page, y is this, and the z is up. This is x, y, z off, and the vector. It's gonna oscillating in this trajectory. Even you can say rotate 3D. Look at here guys. Here we go. See, this is 3D, right? X, Y, Z. If I look at, see, X, Y, it's gonna be like as the butterfly wing, right? If I wanna go to XZ, let me go to XZ. XZ, almost. It's gonna be kind of oscillating like this. I'm not there, but I have to try. Oh, I could catch it. Yeah, this is like as the butterfly that you're looking from this sagittal plane. And if you go to ZY, sorry, ZX and ZY is the same. See, this is the end effector position based on the mathematics. And now this is the omega z of the end effector. The blue line is from the Jacobian matrix that classically I taught you. This is from the angular velocity of the base coordinate system, joint one. They must be same based on the physics of the system. This is how I examine my Jacobian approach. That's right. And now this is omega x, omega y, and omega z. You see that the angular velocities of end effector in 3D space is gonna be like these trajectories. See, if I again rotate this, see, is it 3D? See, it's kind of very interesting. See, in the omega x, omega y, omega z, see, it's like this. And now, but if you look at from top, omega x versus omega y, see, it is like, oh, let's see, yes, see, it's like as this. And if you look at omega x, omega z, close it, it is gonna be like this. So this is 3D. See, this is 3D. This is 3D angular velocities and the vector in the space. And now, interestingly, is that the Vx translational velocity and the vector, Vy translational velocity in y direction, Vz translational, and see that this is very complex profile in space. See, it's very, as it says, if I'm gonna run the simulation, we have kind of the closed orbit of the harmonic oscillation and the vector. Okay, this is very interesting. If you look at from top, Vx over Vy after the vector gonna be like as a lighting system of BMW, huh? If you look at from here, it's gonna be Vx over Vz gonna be like as the, I don't know, it's gonna be like as a hat. And if you look at from this Vy over Vz, it's gonna be like as the wolf eyes, right? So this is very interesting. So it's 3D. So I'm just running this one more time. You see, you can visualize Vx, Vi, Vz of the end effector, and you can see this profile of the velocity, translational velocity. Just look at here at the end effector green point. You can catch it. See that profile? It's very interesting. All right. See, it's coming down, crossing, going X, Y, Z, and here we go. Okay. So I'm gonna stop it here because I don't want to go. No, let me teach you this. Oh, then I'm gonna stop it. Okay, let me just finish this. Okay, so now let me close this. I'm gonna upload this on the Blackboard now. So guys, now after learning this, we are continuing shortly our topic on the redundant manipulators. Why? Because of this. Guys, here for this specific problem, we are done with the problems, right? So we had the V was J in a theta dot vector, right? So here was 6 by, tell me, 6 by 3, here was 3 by 1, and here's 6 by 1. So in this case, I provided these vectors of the joint angles, angular velocities. You multiplied by the Jacobian and gave you the velocity vector. So the name of this, as I told you, is forward kinematic. But in the most of the case, as I will show you in my lab in the experiment, we have the end effector velocities and the coordinates, and we want to move the links that gives me such a trajectory. Right? So we're gonna go backward this way. I mean this way. Right? So here, look at here, guys. Now I want to calculate this time. This is given. This is given. I want to calculate this. By doing that, what I have to do, I have to say V multiplied by J inverse. It's gonna be, or like this. Yes. J inverse in V gonna be J inverse in J theta dot. Now guys, this is 6 by 3. Can you let me know what is the inverse of non-square matrix? We don't have it. We do not have it. We don't. So what's the things that we have to study about redundancy? Redundancy of a robot. That I'm gonna start from the next class. Okay.